All right, so we'll go ahead and get started. If you guys know me, I hate changing the schedule. It is like my biggest pet peeve in the semester, which is why if there's ever an issue, I don't cancel class, I just make a video. But, people get sick. This is what I keep being told. Moms aren't supposed to get sick though, so like we just fake it. But this time it didn't work, so it is what it is. The biggest issue is that now the exam's on Wednesday, which before I was already hesitant about starting a new chapter right before spring break, but it was like 2 days, so I couldn't get away from it. Now it's literally one day. So we're not having class next Friday because there's no point in having class and starting a new chapter and then you go on spring break, okay? So we're having the exam on Wednesday, and don't go around announcing it. We're having personal study time on Friday, okay? That's what it's called because we're not supposed to technically just cancel class. But there's no way that I'm going to start a new chapter with you guys, okay? You'll forget it all. There's no point. So I'll redo the schedule. I'm working on that right now. I did change the deadlines for the assignments on Pearson, so that one's taken care of. But the on Blackboard where there's the image that has the schedule, I'll update that for when we get back. But basically you won't have anything. Once you finish the exam, then you're pretty much done until the Sunday before spring break. You know what? That's when you should do the prep. I'm not going to put it as that, but I would do the prep before you leave so that you're not even thinking about it, okay? But technically it'll be the Sunday before we come back that you'll have the Chapter 14 prep, okay? So that's kind of where we're headed. Today we'll wrap everything up. We'll do quite a bit of practice today just to make sure that you guys are feeling comfortable with those heating, cooling curve calculations. And then we'll do one last topic on phase diagrams, and then we'll be done, okay? What's today? Today's a Friday. Monday is just a review practice day. So just come in with questions if you have them. You don't have to come. It's not required, but come with questions. I can pull up questions from the practice exams. Whatever you guys feel like is going to be useful, that's fine with me, okay? And then exam on Wednesday. Any clarifications about that change in schedule? Okay. All right, so the first thing I want to talk about before we do a long practice problem is cooling curves. It is virtually just, the flip-flop of the heating curve. So now instead of starting with a cold thing, we're starting with a hot thing. And as we progress, we're going to remove heat instead of add heat. So if you had units down here, this would be 10 joules removed instead of 10 joules added. 20 joules removed instead of 20 joules added, okay? And then you can see that it's dropping in temperature, and then also you're still getting those phase changes occurring, okay? So let's we're not gonna actually solve a problem here. I want to walk through how you would solve it, and then we'll do a practice problem where you guys go through all of the steps with a little less involvement from me, okay? So let's pretend we have a sample of water in the gas phase. I'm just gonna say sample. And it starts at 122 degrees Celsius. Okay, so it's been heated up quite a bit past, once it's turned into vapor. And then we want to remove heat so that it becomes a liquid, but we're not going to lower the temperature past that boiling point temperature. So it's just going to be at the 100 degrees Celsius. So what I would like you to do is show me on the plot where it starts. Obviously the temperatures aren't marked out. You can do something approximate though. Show me a dot of the starting point. So we'll call that, point 1, and then show me point 2. And then I want you to just give me the verbally or with equations or something, how you would do those calculations. in order to determine how much, I'm missing a U there, how much heat is removed. Okay? So just take like 3 minutes. You're just doing a description, not an actual calculation. Okay, so 0.1, obviously this is not to scale, so maybe it's somewhere here. It's after the phase change and a little bit of a temperature increase. And then 0.2, oh, it's actually right there where I wrote the 2. So it's after the phase change has completed, but before any additional temperature change has happened. Okay, remember at this point, that's all gas. This is all liquid, and in the middle here, that's the gas-liquid mixture. So we want to be all the way at the end of that spot. So the reason why these can be, so there's 2 types of questions I could ask about heating and cooling curves. One is I could show you a curve and like, I don't know, highlight a particular segment and say like what's occurring at this point, physically, what's occurring at this point. So it could be like, you know, it's a phase change, the intermolecular forces are being broken, something like that. Or it could be the temperature is increasing, the molecules are moving faster. Like those would all be physical descriptions of what's happening at a particular point. Or I could have you do a calculation. If you're doing a calculation like this, I probably am not going to give you the chart itself, the curve itself. Like that's something that you can utilize, but it's not necessary to do the calculation. So my recommendation is if I give you the chart, mark it out like this, because what we see now is that there's like 2 very distinct steps. There's going to be that step and there's going to be this step, right? The pink one, the one that's, you know, a slope, has a slope, is going to be Q equals MC delta T, always. The sloped lines, they're Q equals MC delta T. The horizontal lines, where slope is 0, that's always going to be using either the delta H of fusion or the delta H of vaporization, depending on which is appropriate. Okay? So in these 2 steps, you're going to have, so step, that pink step, that's going to be where you use Q equals MC delta T. And because it's of the gas, it's going to be the C of gaseous water, okay, because those are different. And then for the blue segment, that's going to be delta H of vaporization, because that's the one that deals with boiling and evaporation. The thing to remember about this, though, is that this is the only thing I can really see you guys making a mistake with, if you understand everything. if you understand everything from the heating curves, if you feel comfortable with those, the only way I think you would make a mistake here is by not making sure this is negative. Okay? Because those values for delta H of vaporization and delta H of fusion, those are always reported as positive values. They're just telling you that's the amount of heat. They're not telling you, is it required or released? In this case, it's released or removed. So you need to add the negative sign. In the Q equals MC delta T, that will always come out as negative because the delta T is going to be negative. So you don't have to make it negative. It will be negative when you do the calculation. And you got to make sure that the other one's negative because you want to be adding together two negative numbers. You don't want a positive and a negative because then they're going to start canceling each other out to some degree. That's just not what's actually going on. Okay? They're either both going to be positive or both going to be negative, depending on if you're heating it or cooling it. Okay, so when you have that negative delta H of vaporization, then you're just going to multiply it by the number of moles. There's a chance they might be in kilojoules instead of joules, and in that case, you're going to need to convert it to, we'll just do an arrow, convert it to joules. Okay, you're eventually trying to add these together. You can't add them if they're not the same unit. All right, so that's how you would approach this calculation, two separate steps. Okay, so the next point, this is going to be kind of a long practice. So what I'll do, I'm going to let you take this problem. I'm not going to give you any direction to start. So in a few minutes, I'll go ahead, it says hint, draw a heating curve. I'll go ahead and draw the heating curve and kind of isolate the steps that you're going to need to go through. But take, as much independence as possible on this, so that you feel confident as you get into the homework and the exam. Okay, so go ahead and start on that one. We'll give that 3 minutes. Yeah, so it's not totally an equation, but it's the delta H times moles.
Okay.
Yeah. You just may have to convert it into joules, is the only thing to keep in mind. And if it's in grams, then you would also have to convert it into moles. That's why I said it's not really an equation, because there's all these side conversions.
It's like a conversion factor.
Yeah, it's like, exactly, it's like dimensional analysis. I'll go ahead and draw the heating curve to kind of give you a hint on what's going on with this. Oh, just kidding. Okay, so I've stepped out, shown you the curve, and stepped out the 3 steps for you if you are feeling lost. Okay, so I'm going to go ahead and start working the calculations. If you're doing okay, though, just use them as checking your answers. It's always better to do as much as you can on your own, obviously. Hopefully you Googled this if you needed it, but ethanol is C2H5OH. That should have been in the question. I don't expect you to know that, but you will need to know it for the molar mass. Okay. So I'll leave that up there once you guys are ready to check answers. Yep. The Q equals MC delta T1 is, and like Colton was saying, because the delta H1 is more like a conversion factor, it won't be. Yeah. Was that the same question? Oh, no? Okay. No, so you might have to convert it into kilojoules. It just depends on what the answer is. So since it's multiple choice, check the answers first. And if they're in kilojoules, then convert the 1 and 3, convert those to kilojoules. They just have to be the same unit. So, yep. One of them will have to be converted. Sometimes, though, I'm nice and give you the delta H in joules per mole. And in that case, you wouldn't have to convert either. So. All right, any others before we move on? Okay, so the last thing we need to talk about is phase diagrams, which is actually kind of interesting because all we've talked about so far is phase transitions that occur at normal 1 atmosphere of pressure, okay? Because that's where we're at, and so that's what we're used to seeing. But there is a lot of pressure dependence that a phase change has. So it's going to behave differently under different conditions. So the best example of this is if you think about changes in elevation. So Denver is like, they call it the Mile High City. So it's like, whatever that is, 5,000 feet above sea level. So when you look at atmospheric pressures, they drop as you go up in elevation. This is just because gravity pulls on all the atoms in the molecules in the atmosphere. And so it's holding more of them closer to the center of the earth, to the surface of the earth. And so the further you go away from that surface of the earth, the less of them there are. And then those molecules are then exhibiting less pressure on whatever, your arm, the liquid, water that's surrounding it, whatever the case is, okay? So that's kind of the first thing you need to understand is higher elevations have lower pressures. So let's pretend that the pressure in Denver is somewhere around here. Now, I guess let's just look it up because I was guessing it in my other class. Atmospheric pressure. You got to say in atmospheres or else they'll give it to you in like bar or something in Denver. 0.8 to 0.83 atmospheres. That's actually lower than I thought it was. At some point I thought it was like 0.9 something. So that's interesting. All right, so 0.83 atmospheres. That makes a lot of sense why I'm really susceptible to altitude sickness. So like when I was a kid, our family would go backpacking and we lived in St. Louis, but then we'd go in like the west in the mountains. And so really quickly you're going from sea level up to like 10,000 feet. And it makes a big difference. If you've got, this is just in Denver. This isn't even up hiking in the mountains. So if you've got 20% less pressure, think about how much less oxygen you actually have there. So that's going to make a big difference on how your body responds. Okay, so if we're at that lower pressure, let's look at what happens with the phase change of liquid to gas, so boiling. So let's start by looking at what goes on here. So check out these arrows. Let's just look near the end here. This is the process of warming up a liquid and causing it to boil. So the red line is representative of 1 atmosphere, so we're at sea level. And as we boil, we warm, and we hit a point which is 100 degrees Celsius. So the way you can find things on this plot is just like any other graph. You say, okay, I'm at 1 atmosphere and 100 degrees Celsius, that's this point, or you go to the point and read what the temperature is, okay? So on that line between liquid and gas, that's where the phase change is occurring, okay? That's what that line here represents, okay? That's the phase change. So that's where we're going from liquid to gas. So when you heat something up and you cross that line, the phase change occurs. But what happens if you're at this lower pressure? So I'm going to bring the 0.83 line over. And we see that the point at which it crosses the line is lower temperature. Okay, so now I'm going to Google, what's the boiling point of water? What's the boiling point of water in Denver? Not in Fahrenheit, please. There we go. 94 to 95 Celsius. Okay, so let's call this 95. So it drops the boiling point of water by 5 degrees because that curve, that change in liquid to gas is pressure dependent. So this is why sometimes if you look at like baking mixes, like cake mix or something, it'll have high altitude instructions because it's actually very different to bake something or cook something even. Like pasta would take longer to cook because it's like at 5 degrees lower temperature. Do we get to talk about solutes? I think that's next chapter. I was going to say also, like when you add salt to pasta water, that actually increases the temperature at which it boils. Lots of fun things. Okay, so what else? We can also look at what happens if we keep temperature the same and then we change the pressure. So this line here, let's look at that. This is basically room temperature, and we're going to look at changing the pressure of something. This is probably less applicable to water, but we can use the chart and it's fine. Ignore the arrows because I'm going to do it the opposite direction. So when you have, there's a couple ways you can change pressure. You can change pressure by changing altitude. You can change pressure by actually like pushing on something. So if you have a gas in a container, you can compress the container and make it a smaller volume, if you remember from the gases chapter. It's okay if you don't, because I know some of you guys haven't had that. But if you make the volume smaller, that increases the pressure of those gas molecules, okay? You can also like physically press on a solid. That would increase the pressure. So there's lots of different ways that you can change the pressure. So if we had a substance in the gas phase, now this wouldn't happen with water because we're not going to have gaseous water at room temperature. So let's think of like nitrogen gas. Okay, so we're just going to pretend for a second that this is nitrogen gas. So at room temperature, it would actually be a gas. And then if we were to push on it or compress its container more and more and more, okay, so increasing the pressure, so going up this way, you're going to cross over that gas liquid line. So you can actually cause something to become a liquid, not by changing its temperature, but by just compressing it, by just pushing on it, basically. And we use this all the time, like natural gas that you use to heat your homes and stuff, it's transported as a liquid. So it flows through pipelines and stuff as a liquid. That's because it's been compressed. And then when you finally, open the valve, then it becomes a gas as it expands. If you've ever used like what is that called? Compressed air, just to like clean your keyboard or whatever. It's like a dusting thing. That's a compressed gas that probably is liquefied. In fact, most things that are in an aerosol can like that are liquefied, but they're actually naturally in the gas phase. So the only way that they got them to change that state was by increasing pressure. Okay, maybe two other things let's talk about, and then I'm going to let you guys do this little exercise where you kind of practice going through and reading a phase diagram. So the first thing is, or second to last, there we go. The second to last thing is triple point. So there is a point on for every substance, and you can see this on its phase diagram, where a given temperature and pressure will result in you being able to see all three phases simultaneously. So we can always see two phases if we go to the boiling point at a given pressure or the melting point at a given pressure. We can see solid and liquid, or we can see liquid and gas. But the triple point is where you can have a transition between all three of them. And so that is a very specific temperature and pressure. We never see that for water unless it's under very specific conditions, because it's 0.006 atmospheres. That's an incredibly low pressure. You would have a hard time getting that even in an experimental setting. Like, that's a very vacuum situation where you've pulled out lots and lots of air. We'll talk about the sublimation. Let's go to the next page because I want to talk about the sublimation curve, but it's not really part of water because we don't see water sublimating. So these two, we've got water and CO2 here, so it's a good comparison. So the triple point for CO2 is actually really high in pressure. So for water, it was super low pressure and low temperature. For CO2, it's still a relatively low temperature, but it's much higher in pressure. Okay, so you can kind of see there's lots of different properties between the two that you're seeing because of their phase diagram, or what their phase diagram is showing you. The other thing that's a big difference is the 1 atmosphere down here. Like, so this is 1 atmosphere on water, this is 1 atmosphere on CO2. If you look at all the different temperatures at 1 atmosphere, there's only solid and gas. So CO2 only exists as a solid or a gas at normal atmospheric conditions. And like we talked about before, that would be sublimation, where you cross over this line. Or if you were cooling it, it would be deposition. But this curve, we call it the sublimation curve, that point at which it's going to change phases. And then the last thing, and we'll kind of, this is like the very last text, so I'm basically doing it for you. So if you want to follow along, it's this page here. And there's like a summary of what I'm about to say there, this note. Okay, but if you want to follow along there. So the other way that we look at pressure changes, like I said, is that sometimes you're actually pushing on the thing. So check out where this X is. So we're going to pretend that we went ice skating. So it's cold, you know, it's below 0, and we have ice on the rink. And then we take a skate and you push on the ice. Okay, you apply a pressure. So we can actually look at how that works on the phase diagram too, even though it's a pressure like an actual, like, just in one space, you're kind of cutting into it. So as you apply a pressure, so same temperature, and you apply a pressure, it changes to water. So that's what happens when you're ice skating, is the skate causes enough pressure to compress the ice into water, and then you glide on the water. So interesting, but also what's interesting is that we just said if you compress ice, it turns to water. What that means is that water is more dense than ice is, which is not surprising, because if you stick ice cubes in water, they float. So we know that ice is less dense, water is more dense. But this phase diagram actually tells us that, because applying a pressure, squishing it is another way of thinking of that. If you could take an ice cube and just like squish and squish and squish without breaking it, it would turn into water. CO2, on the other hand, that doesn't work. If you've got solid CO2 and you press and press and press on it, it just stays a solid. Okay? If you had liquid CO2, and you press and press and press, it would actually turn into a solid. So it's the opposite. If you look at it, it's not very dramatic, but the slope of this line is pointing this way. It's a positive slope, whereas this one's a negative slope. So you can actually look at phase diagrams, and if they have a negative slope, you know that the liquid phase is the more dense phase, and if they have a positive slope, then the solid phase is the more dense phase. Okay, so for the next 10 minutes almost, I want you guys to ideally do this with a neighbor, but I want you to go through and work through, it's basically like reading a phase diagram, making sure you know how to read a phase diagram. So go through and answer these questions and like these points on the diagram, and then this one last one is like you have to follow a process, kind of just like we did with the ice skate. Causing pressure, okay? So do that for maybe 5-ish minutes and then we'll go through it. I think these ones are pretty self-explanatory, but I'll put the, answers up as well. Oh, just realized I had those at like 5 atmospheres. Bring that down there. So you're welcome to go once you finish these up, but just this is the kind of thing that you can expect of phase diagrams. Be able to identify things at a particular point, but also be able to look at changes that are occurring as you either change pressure or change temperature. Okay. So the only thing that's not showing on there is just sublimation, if you were following along. What? I thought someone asked a question. No? Yeah.
What's the one on sublimation?
Oh, just right here.
Yeah.
Yep. So that's like this whole changing temperatures for something where you don't get that liquid phase, right? So at a particular pressure.
What solid black line are they referring to?
The sublimation line. So this one here.
Oh, I see.
So each of those lines is where the phase transition is occurring. You don't necessarily have to know that we call it a sublimation line, but just knowing that that's, the solid to gas transition. So once you cross over that, now you've changed phases.